Sweet. Hey class, I'm doing my presentation on AlphaGo. My name is Sir Thomas, and ideally this is called the beginning of the end of human-only intelligence. So a little bit spooky in a sense, right? But this is the first step into like trying to create sentient games, which are like games which are algorithms that can play games and then also extrapolate at a higher level to do things like play multiple games or kind of get into a world of just general AI. So today we'll be learning what Go is, so like where it came from, how the game is actually played, all of the different possible game states, how you start and win the game. Then we'll go into what AlphaGo specifically is, how it works, and the two new types of networks that were proposed in this paper, which were the policy network, the value network, and then how we were able to use both of those to extrapolate features from something that's used in a lot of other models that play games like Go and chess, which would be the tree search. And then after that, we're going to talk about a little bit of what's next. So like where did we go from AlphaGo all the way up to the new state of the art, which is AlphaZero. Okay. So Go itself was created 3,000 years ago in China. It has over 40 million players worldwide, and it's said to have 10 to the 170th possible different game states. So if you're thinking about that, that's basically a 1 followed by 170 zeros. It's played on a 19 by 19 board. Each player takes their time choosing a white or a black piece, and then they basically play them in ways to take over territory. So your entire job is to surround your opponent with your color, and then you basically get to capture that territory. And then at the end of the game, the person with the most territories wins. So what is AlphaGo? It was created by a team in London called DeepMind, which was founded by Demis Haspis, and it was also acquired by Google in 2019. It has a combination of CNNs, basically to be able to read the board state and understand the feature set, then a policy and value network, which I'll get into, and then it uses a specific type of tree search called Monte Carlo tree search. And I'll also get into how those simulations work and why we were able to extrapolate and make the predictions faster using the policy network and the value network. All right, so what is the policy network? So there's a simple abbreviation that we're going to put in for the supervised learning piece, which is called SL. So the supervised learning, the SL policy network, alternates between convolutional layers for the weights, rectifier nonlinear units, and then a softmax layer for outputs, which outputs a probability distribution of all of the legal moves at any particular game state. So basically, we're looking at the map and we're trying to figure out what are all the other possible locations that we can play. It has a 13-layer policy network trained on 30 million different positions. So the reinforcement policy network in and of itself is first trained, well, the supervised learning policy network is trained on all of these moves based on real game positions played by real players, right? So basically it learns the subsets of different moves and feature sets that you can create in the real world. Then they extrapolate that and they use the reinforcement policy network, which basically takes two of the previous networks and lets them play against each other, right? To generate new combinations all to itself. So the reinforced network initialized at the start of the SL policy network, and then it improves its policy gradients by learning the maximum outcomes of winning positions of all of the previous versions of itself. So basically, the reinforcement agent plays against itself to basically create new moves into different feature spaces. The value network. So the value network at that same point is evaluating the board to find all probabilities of winning positions, right? So it basically takes the game state and says, if you play here and then the game ended, who won, right? And it tries to basically optimize you to make those moves. So one is about figuring out all the possible moves, and then the other one is basically to say, hey, if the game stopped at this state, this would be the play that you would take to win. So this is the entire pipeline. So what we're looking at is it takes in the first step in the supervised learning, it takes in human player positions, trains on those, and then we take into the second network is it playing itself to create new positions that are even outside of the feature space of what human players would think about. And then we train the value network on all of those possible outcomes, right? So that it can see all of the different game states that you play along the game, and then basically be able to predict into the future what would be the winning moves, right? But this again is just at the current game state. So basically, if I play a piece, we do policy network and value network of that state, and we only know what's happening in the current state of the game. But now this is going to take us into tree search, which is how we extrapolate the game out forward. So again, if we think about 10 to the 170 different positions, right? Basically, any game state can lead to a bunch of different possible next move scenarios, and then every one of those next move scenarios can lead into another subset of those, right? So it just keeps branching out infinitum, right? So if you think about this, a lot of the current games that play games like chess or Go actually only do this part, and they try to extrapolate the entire possibilities of the game, and basically they pick whatever path gives them the best result before they run out of time, right? So the policy network and the value network are things that we're actually going to use in this to speed this process up, and I'll explain why. So if you take the tree search, right, and you use the probabilities themselves, you can actually optimize to pick moves down the line, reducing the breadth of the tree. So instead of playing every single scenario, you take the scenarios that most likely have the best winning potential, and you optimize for those first, right? So now we've shrunk the breadth of the tree, but we still have a tree that has infinite depth. And then that's where the value network comes in. So what the value network does now is, because it's returning your result gaming end states, right? As you see, you can go down and play out multiple different positions of the game, but let's say we're 100 layers down and you're returning a 1, right? You don't need to return also all of the different states underneath that, because you know you've won at that point. And again, every single time you move from one game state to the next game state, we actually reproduce this entire thing, right? So you don't need the entire game state at any point in time. You just need enough moves to understand where you're going, right? So we've now had width reduction and the height reduction by adding these new layers, which were the policy and the other network. All right. Now, this is a little breakout of exactly how a Monte Carlo tree search works. So what it actually does is the tree search takes the current position and then extrapolates all the moves out, and then takes all of those moves and does it again, right? So it does it in select, expand, and evaluate. So basically, it's basically saying, hey, this one game state brings me to, let's say, 1 million new game states, and then each one of those millions bring me to 1 million times 1 million different game states, right? So like this thing will get really, really big. So that's the reason why we use the policy network and the value network to basically try to attack routes that make the most sense down the path. It was trained asynchronously on a multi-threaded version of the first AlphaGo Lee, using 40 search threads, 48 CPUs, and 8 GPUs. And then they also trained one in a distributed mode that used 1,202 CPUs and then 176 GPUs. So again, the bigger that network, the more of these possible game states it can hold. So what did that lead up to? In about March 2016, AlphaGo Lee, which was the version that was used to play Lee Sedol, who was at the time the 18th world record title holder and a 9 Dan player, it beat him 4-1.
Oh.
So basically, that was the point when people started saying, hey, the general AI is coming to kind of take over, and then we kind of went into like this kind of scenario where everyone's like, this is the beginning of the end. There was a lot of like press releases and articles around that time that came out about this. And then lastly, the question is, what's next? So AlphaGo Lee was that current version, and then right now we've extrapolated all the way out to AlphaGo Master. Some of the differences there is Alpha Zero, which is the current state of the art, solely learned from playing by itself. So it basically kind of start out in the way that we were talking about with the Deep Racer, where it has no knowledge and it just starts figuring out the board and then how it should play. It only takes in the raw board data as inputs. The policy and the value networks were actually combined, and then they used ResNet architecture to be able to like pass through more information from the CNN. And then there's no Monte Carlo rollout anymore. So it's just the evaluations of the policy network and the other network that does search-based policy evaluation. It uses the convolutional network and the ResNet to pass in a lot of that data so that there's no cold starting problems. And then it's a lot more less specific than AlphaGo Lee, which was trained specifically after other real world players. So it has the ability to be more generalizable, and then they actually took it to play other games. So it was also trained to play shogi and chess. In about 4 hours, it became a chess master. In about 2 hours, it became a shogi master. And in about 8 hours, it was actually able to beat AlphaGo Lee. So these are multiple different games that this thing is able to play. After 40 days, it actually became the most powerful version of the Alpha series. So there's AlphaGo Lee, which is the one that beat Lisa Dahl. Then there's Alpha Master, which is when they started using the ResNets. Then there's AlphaGo Zero. Then there's Alpha Zero. Alpha Zero is the one that was basically trained completely from scratch. And Alpha Zero is classified as an 11-dan player. So it's 2 levels higher than the best human player, and there are no other humans actually in that level. So there's no humans in level 10 or level 11.
Okay.
It's only AI. So if we think about that, the next thing is, right, if we can beat humans at higher level intelligent games, OpenAI took a lot of that research and they created this thing called Shadow Fiend. In November of 2016, they had their first commit, and then I think that's 10 months after, they actually were able to beat, they had hosted a game called the International 7, and they were able to beat the 7 best Dota players in the world using another AI that's incredible. So it's like, once we've beaten adults, let's beat some children at video games. And then here's some of my research. So I'll share these slides, but a lot of it is basically like, there's actually a documentary on AlphaGo, the team, how they actually built out the process. And then the paper's actually also in there. And then if you have any other questions about just generalizable AI, feel free to contact me. Thank you.
Yeah, thank you so much. Questions?
Questions?
Yeah, probably you can take some time to think.
Mhm.
Yeah.